thank you so much. I really want to thank IPAM for the chance to come over and talk with everybody. I just had a little baby, so it's been a blur, but it's been great to be here. So I always have this, I think to this community, maybe it doesn't make a lot of sense, but I'm going to show it anywhere. I would say when as a material scientist or a chemist, a computational scientist, we've got a tool and we've got a number of ways to help, right? We can simulate nature with the laws of physics that extrapolate. Might be too expensive or maybe not. The simulations may have some cost. They will definitely give you back the physics you put there, right? That's why they extrapolate. But they're also constrained by the knowledge, the prior knowledge that you had about the universe you're simulating. That's on one end of the spectrum, right? And what the simulation is depends on what scope of matter you work at, right? Some people do, crystals, coarse-graining, grain boundaries, metallurgy. For me, this is atomistic simulations. This is electronic structure, a little bit of MD. And the other end of the spectrum, we've got also computational tool, which is what they used to call data mining. And some reviewers still say, this is the data mining paper. It's not called that anymore. But statistical learning, right? Let's use data. We don't have a lot of understanding of the underlying laws of what's governing this, and we can use computer-based methods to study and interpret and predict and design. And then there is something in between. This is this synergy, and to this audience, I think it's pretty obvious. There is many ways these two things can talk to each other by putting our priors, the laws, universal laws into machine learning, the symmetries we know, or the other way around, accelerating the boring, repetitive part of simulations that we've calculated over and over again. And the way I personally arrived to this field was through high-throughput virtual screening. This is something that Alan, of course, pioneered in organic materials. That has a long history in pharma, which is making some big virtual library full of candidates for something, and then evaluating them with a computational deterministic function, right? In our case was electronic structure simulations. Some people fill their database with crystals. We filled it with molecules. We calculate, we start with 1 million, calculate maybe 100,000, find about 1,000 that are, worth showing to people because they hit all the milestones that our collaborators wanted, and a little tiny fraction of them gets made and perform well and validate the approach and hopefully move the needle forward in some field. And two examples of these where this has worked to some degree was in organic light emitting diodes. These are the materials that make most of the Samsung phone displays, for instance. The new iPhone 11 Pro has it, but 11 doesn't. So it's this high-end luminescent material for displays, these big TVs, and it has really good properties. It's made of molecules, and you can simulate it. So we ran a big campaign. We simulated tons and tons of molecules, and we traced what were good. Another place where the same platform worked was designing molecules for batteries. This is for large static batteries that could store, the amount of electricity coming out of a wind generator for a day. So this big tank-based storage. And the same, what is the best molecule we could possibly put there that has the right electrochemistry, the right solubility, and these are things that you can calculate. And this gets you these maps of chemical space where we know we've got some properties that we care about. Here we want to go up there to the top left. Here we want to be in these boxes that I drew. So we get these big maps of chemical space and properties, and we can tell our collaborators, well, go make the orange ones. All the red ones were already made by somebody else, so we can trace chemical space. And in the process, of course, we compile these large databases of molecules and labels, computational labels tied to them, that are also pretty much noise-free, right? They're atomistic simulations. They may have bias with respect to the experiment, but they have numerical noise, in double precision. So these are very good data sets. And one of the first things we started doing was skipping the simulations altogether, right? Instead of, running all these simulations over and over again, train interpolating functions that for a new molecule will tell us what the calculation would have said. And if it's really terrible, we save ourselves the calculation. And this has come up a bunch of times here, but the graph convolution neural network has been the workhorse of how we've approached this problem. And essentially here, to to refresh it for everybody, is that every atom in your molecule is a node, and it exchanges informations, features, with all the nodes that surround it. In molecular space, probably it makes sense to have the information flow across covalent bonds, but you could also make, as we heard yesterday, a fully connected bond where every atom talks about with every other atom. And then, there is an update function. All of these are neural networks. The update function decides how the messages from every other connected node gets added to each individual node. If edges have labels too, they can go in. We can have attention to decide which connections are worth following, etc. And I've got a couple of controversial statements that could drag us into a rabbit hole. So I'm just going to say the question of, for predicting molecular properties, what's a property of the graph? They will call 2.5D, because the chemists have graphs with chirality, which is it's a 3D property, but we can more or less embed it in a graph notation, or cis-trans stereochemistry. That more or less can be embedded on the graph. There are 3D properties. This is what is the 2.5D. But most of the regression one does over molecular space is done over the graph only. For instance, things like interatomic potentials are something where we study the energy as a function of Cartesian coordinates. So that, of course, needs the Cartesian coordinates. But I think there is different sets of people that have, care about different things. And I think this is one of the blocks that makes different what some people are interested in. In the topic of interatomic potentials, we've got, I don't know if Alexander Tachenko is in the audience. Yes, we got a great introduction. He gave us all the benchmarks, and I would just said that, it's absolutely true. It can get to work. If you train on the right ensemble, and you sample on the same ensemble, 0.1 kilocal per mole, same amount for the forces, so it's as good as it gets. That's way better than the chemical accuracy. It's getting to almost not quite, but close to the numerical noise of the DFT that you would be running, maybe. With the keyboard, those tools, we've done a lot of this thing, right? Where we have a molecule, and we've also heard a lot about this, but I will remind us that the forward problem, filling a box full of molecules and sorting through them one after the other, is one way to do it, and it's worked, right? It's the full enumeration, when it's a few million. We can totally have databases with a few million. We calculate some, use a surrogate function for the others, maybe make some epsilon greedy or some Thompson sampling to go through that database with some clever strategy and find the best. But ideally, we would want the opposite. We would want the inverse design approach, and like you would say, sampling around, like maybe experimentalists do in the lab. No experimentalists in the room. Can I say this? That people, sometimes it's not clear what the strategy was for the search when they give you, can you regress over this data set? It's like, you run the same experiments twice in 2 months, you didn't even realize you were repeating. I've had that happen to me. Or high throughput, we do a grading chemical space, and we just try to find good properties. Or we try to have some analytical response function that we invert or locally optimize, right? Have some response function. And this is something that, it's somewhat superseded as this particular implementation based on SMILES, but the approach, I think, still remains. Getting some molecule, sending it to a continuous representation, where in principle, it's smooth. In principle, we can do gradient descent for optimization. In principle, we can sample new points that always become new molecules that are interesting, and essentially do inverse design chemical space. And we've seen good direct law, but I would also want to show you the bad direct law. This was the reaction from the highly respected medicinal chemist bloggist, who argues, and it's a fair statement, that lead discovery may not be the problem, right? That there is other issues, and they're just spamming these guys with a host of leads is not necessarily solving all the problems. And maybe, Woodward said it, I don't think he even said it about simulation. He said it about physics in chemistry, just about sitting down and writing a model, the electron hops between orbitals, but still it's the same. it needs to work in the lab. And I think it's on us to find the collaborations, find the tools, find the data sets to make incremental but sizable contributions, right? I mean, and Alexander today was a great example, right? With the molecules that work, that were made, that were tested, and sort of really help move the needle somewhere. Like Glivec, right? Glivec was the milestone for computational design. It will be, we're looking forward. Hopefully, a person in this room makes the next FDA-approved drug that came from a regressor. So where are we right now? And so one of the things we're interested in is this dimensionality reduction in 3D space. Right? It's essentially a similar idea, and we call it coarse-graining in molecular dynamics. Typically, when we simulate a chunk of matter in materials, we decide a system with a nanometer cube contains about 100,000 atoms. And then we sample the properties of this system by exploring how they evolve in time, 1 femtosecond at a time. That's typically the scale of how one simulates matter. So ideally, we would like to either simulate fewer particles or move them faster, so we can accelerate and access the time scales where things happen. Imagine, right, like when you're maybe crystallizing a polymer, melting a solid. The length scale of those processes has, we can attain that. We cannot get there with simulations for most problems. And the way people address this problem is what they call coarse-graining, which is deciding, what, I'm not going to simulate all the atoms that make up my system. I'm going to assume that some of them move collectively, and that I can suppress their collective motions and represent the set of connected atoms with one superatom, with one bead. And we typically do that so that we reproduce the structure of the system we're trying to study. And the statistical mechanics of this is fairly well understood. This is something that folks have been thinking about for a long time. And there is a number of ways to do it that are typically very involved. They typically require you to decide on some coarse-graining function, so which atoms belong in which superatom. That's one decision that a person makes. Then forces you to simulate the system, again, for the duration to achieve some thermodynamic equilibrium, and then see if you recover the right structure. Does my coarse-grained system recover the structure of my all-atom system? And if it doesn't, update and repeat. And someone has done us the favor of parametrizing something and making it available for the community. But of course, the transferability of these pre-baked efforts is not great. So then everybody can use them, but they don't really solve anybody's problem. And if you think about it in terms of a learning problem, essentially we've got two coupled learning problems. One learning problem, which is which atoms should I couple together, right? Like, all atom. This is what they call united atom. This is the first most obvious way to coarse grain, which is, these hydrogen atoms that are vibrating. They have the fastest vibrations, so they're the guys responsible for us taking these femtosecond steps, and they're also all connected to their heavy atom counterparts in very obvious ways. So the first thing, and people don't even call this coarse-graining sometimes, they just call it united atom models. The next step is to do functional groups. And then what is a functional group? Well, a chemist comes here and says, what is a methyl, diamide, or we can go all the way up to amino acid residues. So this is a decision. And the way we thought about this is, and other people have as well, is as a learning problem. So we've got two things that we're going to learn. Our original data was sampled, our training data is going to be Cartesian coordinates of atoms moving in space. And there is a potential that allows us to get the forces acting on them throughout this trajectory. And the thing we want to learn is a coarse-graining function that, given the all-atom representation, gives us the best way to group atoms together, and a coarse-graining potential that allows us to get forces and run dynamics on the coarse-grained representation. Right? So these are the two things we would ideally like to learn at the same time. The VCG, the potential, is something that there were all ways of doing it, and that's how they anchored in, I think, in ways that are not arguable, the stat make of the problem. But the decision of how to discretely send these all atom sets to united atoms, to beads or superatoms, is up to us. The form of VCG. In material science, for sure, these VCG are typically very simple functions, so that we can evaluate them very fast, and they're also very local. Typically, the beads in coarse-grain don't talk with large chunks of the system. They're usually very local functions. So one can decide to use classical terms. You could write a harmonic oscillator, a Lennard-Jones potential, maybe a Morse potential that is more anharmonic, or use some form of mesh spatial neural networks, have a interatomic potential. The ones we've said are really, really good at learning energies. We'll use one of those to learn the coarse-grain energies, and we'll see that this is really important. So how are we going to do this? The way we're going to make this work is doing something called force matching. And in force matching, what we do is that we force the minus gradient of the coarse-grain potential to match the mean force that is acting on the superatoms. So we know from our training data that this was sampled. We have forces available to us because this was sampled with molecular dynamics. So our labels, our training data has structure and the forces acting on these atoms. That's how the data was acquired. So we're going to use the forces to obtain a mean force acting on this bead, and then match it to the derivative, the minus derivative of the potential. So this is where we're going to try to optimize how the forces match. And the rules of coarse-graining, in order to conserve the definition of momentum, mean that this is a discrete choice. An atom can only contribute to one coarse-grain atom, right? So we can't have the atoms smeared out across the system. Each of our full resolution atoms can only go to one superatom. But learning discrete structure is something that, has become possible in the last few years. We use Gumbel softmax, which starts off with a continuous distribution, and then as we move the temperature down, as we cool the system, it gets more and more discrete until we finally sample a mask. So every atom can only go to a choice of superatom. That's the most special thing, and then we make this function linear. So it's just a linear transformation. It's just a linear operation. And then the next definition is, what is this mean force? Okay, so this mean force should be, in principle, the potential of mean force. So in principle, it should represent the derivative of the free energy of the coarse-grain particle, which means that we should run constrained dynamics for every E of C that gives us a Z, run the full dynamics, I get the free energy of that surface. But that would go against what I just said we wanted to do, which is do this in one shot. So the way we're going to do it is to use stochastic force matching using some instantaneous version of the mean force. So this is just a function that is derived. It's here. This is how typically B is described, the force coarse-graining function. This derivative of E transpose, that's a choice. There are other functions that would have the same mean, but different choices for this term. But that doesn't matter. As long as they all have the same mean, the choice is ours to make. So we choose that, and we're going to match the transform forces. So we got the all atom forces, we transform them through E onto the coarse-grain representation, and then we force them to match the derivative of the coarse-grain potential. Okay, so got this part. This is a sensible loss, but I said I was borrowing from auto-encoders. So we got our supervision, but there's a little bit missing, which is our reconstruction. Ideally, and this is not the case for everybody that wants to coarse-grain, but ideally we would like to recover atomistic resolution from time to time. And this is interesting for some reasons. For instance, when we're doing electronic structure, imagine we want to know how charge move across a material. There is two decoupled timescales. One is the timescale for us to understand the morphology of our system, and that we can use coarse-graining for. But then to understand how charge moves around, we probably want to know the actual position of all the atoms. So we want to be able to crack open these grains and get the atoms that were in there. And we're doing that just with a, again, another linear transformation that for every coarse grain position, E of x would be z. D of z, we try to have it reconstruct the original data, right? So that's the process. Essentially, yeah?
So is this decoder probabilistic?
No. So this ties with the Boltzmann generator that we saw yesterday. In this case, we're learning a mean, right? We're always decoding deterministically to the best possible mean, understanding there is some information loss. Well, with coarse-grain, there is information that went away, and we're not trying to resample it stochastically. We're trying to reconstruct the mean. And the follow-up, you just hinted at it, would be to try to reconstruct in a stochastic fashion.
The mean may be a very high energy conformation, right? If you have sort of two favored positions, the mean can be the terrible thing right in the middle, right?
You haven't seen these slides yet, have you? No, that's exactly what happens, yes. So it's, we need to give it a little bit of help. So there's two ways to avoid that. One is sample, giving it some noise so that it goes one way or the other, or giving it a few more particles for a reference, for a frame of reference, so exposing a bit more information about the context so it can break the symmetry when it can't make those decisions. But yeah, that's spot on. So this is the pipeline, as I was saying, right? We get our trajectory, we shuffle the frames, which means the kinetics just went away because our data set is going to see subsamples of the trajectory that give us okay instantaneous means, right? We want our instantaneous mean force to be as good as possible. But by doing that, we just, we're trying to learn a structure, but we're not necessarily going to learn kinetics. And then we train the compression function and the potential in the coarse-grain representation at the same time. And then we go run the CG and see if we get what we expected to. Just to give an idea of what this reconstruction is doing, this is Alanine Dipeptide. We don't even have forces here, we're just seeing what this 3D autoencoder is doing to this Alanine dipeptide, to the dihydrals, and exactly what you just said happens, right? Like if we coarse-grain to 3 particles, it doesn't recover any structure, it just doesn't know, and we're not giving it any noise to break symmetry, to decide, but the moment we go to this 5, it starts doing an okay job. This is all atom, and this is slightly less than united atom. So this is 8, united atom would be 9, so it's kind of it's a choice, and that's the beauty of not having to decide. You just have a framework that can automatically assign what the most important bits are and recover structure. So for a single molecule, this is how the cycle looks like. What we're seeing here is the weights of the coarse-graining function that are, for all these atoms, deciding to which coarse-grain particle they belong. And as we lower the temperature and discretize the selection, we force them to go to a certain direction. And of course, this is an easy example. The choice here is reasonable, is to go with 1 bead for every particle. And then the dimensions that are left for us when we run simulations in CG to recover, of course, are these 2 distances and the angle between them, and they're recovered correctly. A little bit more on reconstruction, right? So this is the same story. 2 particles, 3 particles, 4, 5 for this triphenylene, or 2, 3, 4, or 5 for aniline. And one of the things we see is that, the moment we get enough particles to break the symmetry without adding any noise, the reconstruction loss gets pretty good. So we can pretty much reconstruct okay. But something that we also observe, this is the instantaneous force. So I said, in the unsupervised part, we can learn a coarse-grain mapping, and the coarse-grain mapping, without us training a VCG yet, just having a coarse-grain mapping means that there is a instantaneous force, right? This is the transformed version of the all-atom force. You can see how the instantaneous force gets higher and higher as we have higher and higher resolution, because we're not here we're not averaging out anything anymore, right? So here we were averaging all the motions, so we had a very smooth potentially surface, and as we have more and more atoms in the CG representation, we see more forces trying to push all the atoms in all the directions. And this is a added term that we're going to use. So this borrows, if you want to think about it in this way, from gradient domain regularization. So this would be having the coarse-graining field that gives us the least fluctuating instantaneous forces, right? In the generalized Langevin equation, the friction and noise term are going to be related to the difference between the instantaneous force and the actual mean force. So the error we're making by mini-batching is related to this gradient domain regularization, right? So we want to have the least fluctuating possible potential area surface. Oops, I'm sorry. So the potential area surface with the least possible fluctuations. So that means that we're really learning the slowest motions, right? We're sacrificing the things that beat fast, and we're learning the things that move slow. And for instance, this is an example, right? This is raw. This is how much we want to just reconstruct versus how much we want to have low forces acting on the coarse-grained particles. So the same aniline can be coarse-grained in two different representations, right? One is smoothly distributed that has, 3 atoms on half of the phenylene ring and the other half with the nitrogen. So two, let's say, equal in size coarse-grained particles, but then the forces acting on these guys are much higher. You can see, right, this distribution of states is much tighter. The harmonic bond that connects them has a higher constant. So it's exploring less phase space because it has very strong spring constant. Or the partition that chemists would have intuited is the one that has the least fluctuating forces, where all these guys move collectively, and then these two guys have a motion with respect to the other. And here's another example with two coarse-graining fields that have the same reconstruction. These and these are just as bad to reconstruct. But of course, the forces acting on these beads are bananas because they're not capturing the collective motions correctly, right? They capture, the neural network is able to reconstruct, but it doesn't capture the collective motions. And this is the one, and this is, what folks have been doing in their heads, something that can be reconstructed and is capturing the collective motions. So with this extra term, that makes our life really easy because the coarse-graining field now is almost, automatically learned, and VCG falls out of it. These are some results that we get. So this is liquid ethane. So this is a molecular liquid. So here we try to learn a good classical potential. This is how people would have done it with a harmonic bond and Lennard-Jones terms in between the beats. And the best classical potential is already, it's okay. I mean, it learns the right mean for the bond, and it tries to get the width correctly, and gets some of the features of the radial distribution function, but it's already not enough. And what we've done is really just united atom. So we've run a very mellow coarse-graining, and we're already having trouble with a classical potential in reproducing the structural features that we were supposed to learn on. Now, if we learn a neural potential, suddenly it's much, much easier, right? So this is the potential that got learned for the harmonic bond, for the bond. And you can see it's mostly harmonic, yes, and it has these few little kinks to represent the many-body interactions that went away in coarse-grain. And of course now, that works, like it learns exactly the radial distribution function because it's a pretty easy problem. Kinetics, what happens to kinetics? Well, that was never in the works. We never tried to make this work for kinetics, and what happens is what always happens in coarse-graining, very often, that the kinetics suddenly became much faster. We've taken a lot of modes out. There was a lot of friction. We haven't put it back into the generalized Langevin equation, so we're running regular dynamics, so they run much, much faster, which is, this is not a huge issue because that's not what we were trying to do anyway. We're trying to accelerate dynamics, so the fact that we can attain the right structure faster is not a huge issue, at least if we're just interested in a structure. This is a slightly larger problem. So this is 120 carbon atoms of polyethylene that go to 8 beads. Why 120 and 8? Just to show some discretization decisions. So this is how they end up going as we run more and more epochs and discretize our choices. And for an example in bulk, so material science now, this is C24. So this, I don't think it's, I'm not sure if it's a solid or a liquid. It's something in between. So, 1 in 2, 1 in 3 compression, it's up to us. That's the degree of freedom. That and the form of the potential. If it's just a neural network, then a lot of freedom. If it's classical terms that one chooses, then it's going to transfer really well, but it's going to struggle. And then we recover the structure as we expected, right? Like the end-to-end distance is really good. The bond distance in the coarse-grained representation is also good. And the kinetics are not too messed up. I mean, these kinetics are really, really good. It's random. It's fortuitous. We just got lucky. But in general, right, we're in the same general universe for getting the kinetics. And then I think I've got a little time. So this is our only first and so far only sortie into neural potentials, and it's based on something very practical. So in batteries, when you're trying to make a lithium-ion battery, you need an organic that shuttles ion from the cathode to the anode, right? And I mean, you've seen in the news, it was the Samsung phone, now it's the MacBook. There are lithium batteries that can catch fire because the molecules, the organic in them are liquid molecules that don't have a lot of mechanical properties. They're liquid, they have no mechanical properties. And they can catch fire when the lithium and the organic are in contact with air. That's a recipe for a fire. So folks are trying to find what is good ways to have organic molecules that chelate lithium. So what we want to have is an organic that wraps around lithium. So it's a, pre-constrained chemical space. We're going to look at molecules that look like this, ethers that have oxygens in their and carbons in their backbone. And the question is, what is the strongest we can bind lithium with one of these structures, right? And so we want to explore the configurational space. And these are small molecules with molecular dynamics. We can definitely explore the configurational space and find which are the guys that bind more strongly. And the chemical space is not huge, right? It's this interaction that is, electrostatic. There is probably some polarization of the lithium on the oxygen atom, so it's not exactly classical, but it's not very difficult to learn. So this is what we went out to do. So we, did what most people would do, which is we started with some geometries, displaced them along the normal mode to explore a little bit of phase space, and train a potential over that geometry set. And the held out validation is 1 kilocal. It works great, right? Like it definitely learns that ensemble. It learns that part. But then we try to run dynamics with that, and we validate what the actual DFT forces were on the newly acquired geometries that we explore with dynamics. And suddenly it's catastrophic, right? Like it's 5 kilocals on the energies, 20 kilocoulombs on the forces. So the held out validation was, was part of one ensemble that we learned really well, but that wasn't the ensemble that we're sampling with molecular dynamics. So we had to, do a series of rounds of evolution of this. So that null data that we didn't validate great against, we put it in. We train a larger network with, it's a little bit more data, and we keep doing that until convergence or until we get bored. Each one of these was about 1,000 or I think 1,500 atoms, and the first one was 25,000 or 20,000. So it wasn't really the amount of extra data, but the fact that we were doing inference on a different ensemble than we had trained on. And some of the standardized data sets to train neural potentials for the benchmarks come from really good samples, right? They come from nanosecond samples of a small molecule dynamics. So it's a very good ensemble that was trained on. So the sampling represents that the inference happens on that same ensemble. But for us, it took a few rounds of having this thing evolve. And this is how the regression curves look like. Like this was the forces, and this was the energies for the first generation. And this is after a few more generations. So So now that we're certain that these things hold and we can explore phase space, then it was not too challenging, right? We run molecular dynamics with the small molecule and the lithium. From time to time, we take frames and do gradient descent to see what is the minimum that they explore. We find all these minima for a bunch of chemistries, and then we compare the binding energy, the lithium binding energy, which is the thing we want to maximize, with the DFT, with the reference. And in general, it works pretty well. All the red ones are chemistry that were not in the training data of the potential. The chemical space transferability, I think we took for granted, but it looks like it works well. It's very constrained chemical space. But the configurational space transferability was a little bit of a challenge. This I just throw because it worked really well. I don't know if people typically sample the Hessians of the learned potentials, but in this case, the Hessians look really good. So we'll even for the imaginary frequencies. And then, for this community, I think the fact that we found a bunch of organics that are stronger binders is not the main take home, but hopefully, we can move the needle a little bit on batteries, knowing more about this binding. And with this, I thank these two guys that did most of the work here, and our sponsors, and you for your attention on the last talk of the day. Cheers.